Okay, we're going to start with the definition here.
So we don't have a list of names.
Have we already paid
The shirts, no, y'all just paid for dues. We have a design, but like, we need to get it ordered.
I thought that's what Samara was
She got the design and asked Sloan if he could do them. We just don't have a list of names of who's actually in NHS and who's not. Because I said they were gonna review from last semester and then they didn't.
doing. Oh, yeah.
So it's not
Because
really
the
our
senior
fault.
did the research.
I mean, it's not the rig office, one of them. We can also ask her that. Yeah, I also got that, that question. I'm like at 5 hours already, but. Yeah, I came to the pageant. I sat,
The ball game.
yeah, we just sat there, there was 4 of us, and we sold roses. That's another 4-person job whatsoever. So we just kind of sat there and talked. It was great. Mm-hmm.
3:30. 21.
Okay, I'll give y'all a second to copy this and then we'll talk about what it means.
You sore from playing?
I was. My legs were really tired still, and then I went to the gym yesterday and we did legs, and now I'm really feeling it.
But I was not tired yesterday at work because I was so tired.
Oh my gosh.
Because I got up to go to the gym before school and I had class at 8. And then I did legs and like
Same girl.
legs.
Yeah.
And then I'm on my feet the entire time. The 6 hours I'm at work and I was like, no, that's not it. We got out late last night too and I was so mad.
I didn't realize how tired my legs still were from skiing until yesterday. And I was doing lunges and went lunged down and could not stand back up. I was like, okay, they're done. My muscles are jello now. Thank you.
No, I'll do like the bike sometimes and like I'll be on there and I'm fine because it doesn't really hurt when you're doing bikes, but you get up and like you can't stand up straight. Like I'm like, oh crap.
How much is it?
$22. What?
Is that on the base?
No, it's the black card. Like I get access to the massage chairs, the hydro, the tanning, all that. And you can bring a person for free. Like it's really not bad.
Okay, let's talk about this chain rule. It says, suppose that we have two functions, f of x and g of x, and they are both differentiable, which means you can take the derivative of both of them. If we define f of x, capital F of x, equals f of g of x, which is the composition of functions, then the derivative of capital F of x is the derivative of f of x times the derivative of g of x. This seems really complicated. It's not, I promise. I like to think of it as outside function and inside function. So like when you have a composition of functions, it's a function of a function. So there's technically two functions at play. To take the derivative of something like that, you take the derivative of the outside function, leaving what's inside the same, like this g of x doesn't change. Then you take the derivative of what's inside and you multiply. So we'll do an example. Hopefully that'll help explain what's going on. Okay, example 1, use the chain rule to differentiate r of z equals the square root of 5z minus 8. Okay, so there's two functions at play here. The first one is this square root function, and the second function is what's under the square root, 5z minus 8. So to take the derivative of r, we take the derivative of the square root, leaving 5z minus 8 as is. Then we take the derivative of 5z minus 8 and we multiply. So let me write it like this. First of all, taking the derivative of a square root function, we always rewrite that as a fractional exponent. So let's go ahead and do that. So instead of the square root of 5z minus 8, we have 5z minus 8 to the 1/2 power, because we have a power rule for derivatives that we can use. So the 5z minus 8 is what I'm calling our inside function. And the exponent of 1/2 is the outside function. So when we take the derivative, so r prime of z, we're going to take the derivative of the outside function, which is this 1/2 power. So to take the derivative of an exponent using the power rule, the exponent comes down in front. So the 1/2 power comes down in front. The inside function is going to stay the same. So it just stays 5z minus 8. And then we subtract 1 from the original exponent. So 1/2 minus 1 gives us a new exponent of negative 1/2. So right now what we have is the inside function, 5z minus 8. And we left it alone. We didn't do anything to change it. The 1/2 in front and the new exponent of negative 1/2. However, you need to draw arrows to these. This is the derivative of the outside function. So we took the derivative of the outside function, leaving the inside function alone. But then we're going to multiply that by the derivative of the inside function, which is 5z minus 8. So the derivative of 5z minus 8, we take the derivative of each term separately. 5z, the derivative is just 5. And the derivative of negative 8, the derivative of any constant, is 0. So really our derivative is just 5. So this is the derivative of the inside function. Okay, so we can just rewrite this a little bit. We can multiply 1/2 times 5 to get 5/2. And then we usually don't like to have a negative exponent in our answers. So we can take this entire term and put it in the denominator, and that will make this exponent positive. Anytime you move a term from either the numerator to the denominator or from the denominator to the numerator, moving across that line changes the sign of the exponent. So to change the sign of this exponent, we just need to move this term to the denominator with the 2 that's in this denominator already. So what's going to be left in the numerator is just 5. And then in the denominator, we have the 2 still, and then we moved the 5z minus 8 to the denominator so that that exponent would become a positive 1/2. And this is fine as it is, but since our original function had a square root instead of a fractional exponent, let's go ahead and change that back to a square root. So we have 5/2 times the square root of 5z minus 8. Questions about this? The chain rule. Well, it's not. We're still just taking derivatives. It's just another rule for like a function inside of a function.
Just like the exact first time we did derivatives, except instead of the second part being to the side, it's smack dab in the middle of the first part.
Right. We just when we used the power rule before, it wasn't on, there wasn't a function inside. It was just like X or like.
But if you can just learn to ignore that first part and then until you're ready for it, then this is no different than anything we've done so far.
So what Dakota's saying is you guys should not struggle with this at all because it's the same. So I'm gonna hold y'all to that. No, really it is. You're still just using the power rule like we always have. We just have an additional step, which is to multiply by the derivative of the inside function. And technically we were doing that up until now. Like if we had x squared and we took the derivative of x squared, we moved the exponent down. Our new exponent is just 1, so we don't have to write it. But if we multiply by the derivative of the inside function is x, and the derivative of x is just 1. So we still end up with just 2x. So up until now, the derivative of our inside function has been 1, or something that wouldn't change the derivative anyway. So it hasn't been mentioned, but now we're getting a little more complicated. How about some more examples? Example 2, we got several parts to this. We're just gonna power through some examples here. Okay, example 2, part A, we've got f of x equals sine of 3x squared plus x. So we want to take the derivative, f prime of x. So you guys tell me, what is our inside and outside functions here? What's the outside function? Sine. So the inside function, 3x squared plus x, yes. So taking the derivative of the outside function, the derivative of sine is cosine. And when we take the derivative of the outside function, the inside function stays as is. So just 3x squared plus x. That's the first part of this step, taking the derivative of the outside function. Now we multiply by the derivative of the inside function. So now we take the derivative of 3x squared plus x. So the derivative of 3x squared, bring the exponent down in front, it gets multiplied by the 3. So 2 times 3 is 6. And our new exponent is just 1, so we don't have to write it. Plus the derivative of x, which is just 1. So we've got the derivative of the outside function, leaving the inside function alone, times the derivative of the inside function. Okay, we could leave it like this, but normally if there's a trig function, whatever comes after it is a part of the trig function. What I'm trying to say is we don't want people to think that we're taking the cosine of all of this, because we're not. We're only taking the cosine of this first set of parentheses. So to make sure that that's not misunderstood, we usually want to write anything else in front of the trig function. So we would write the 6x plus 1 first, then cosine of 3x squared plus x. Just so there's no confusion about what's actually included in the cosine function. Questions on this one? All right, part B. F of t equals 2t cubed plus the cosine of t all to the 50th power. For your wisdom teeth. I was like, you can't just say that. Like, I'm gonna just make a quick phone call. It's nothing to do with what you just said. Anyways, part B. So what you're saying is you're not gonna remember any of this. Okay.
I mean, I'm not taking drugs and I probably won't remember it.
No.
You're doing good this homework.
Thank you.
I understand it. Will I remember it in a week? Probably not.
Well, there's not much I can do about
Yeah,
that.
exactly.
I can't help your brain chemistry,
Not
sorry.
your fault. I mean, like, I'm following and I'm really not trying because I know I'm super brilliant in it. So you're doing a great job.
What you're saying is I need to just give a bunch of homework so that it's drilled into you.
Did I not tell you that I'm working like 30 hours this week? I've already got like 4 assignments and I don't know when I'm gonna find time to do
You
it.
know you don't want to do that because then you gotta grade it.
Yeah, that's nothing. That's my job.
Why make it harder on yourself?
Okay, well, you guys tell me how to do this then. We're taking the derivative. What's the outside function? The exponent of 50. So how do we take that derivative?
That's a good question.
Yep, the exponent comes down in front. What happens to what's inside the parentheses? Stays the same. And then what's our new exponent? 49. Okay, so that's the derivative of the outside function. Now we multiply that by the derivative of the inside function, which is 2t cubed plus cosine of t. So what's that derivative? What's the derivative of 2t cubed? 6t squared. I'm trying to enunciate better. 6t. Okay, plus what's the derivative of cosine? You guys remember that? It is sine, negative sine. Let's see, let's go ahead and just change this then. Instead of saying plus a negative, we'll just say minus sine of t. There's not really a simpler way to write this, except we could just leave out this multiplication symbol. So if you want to just erase it, that's fine. I'm going to rewrite it. Really, when you're working these, you wouldn't even have to write this multiplication sign in the first place. The only reason I do it is for reasons that we talked about in part A, so that I don't confuse myself and attach these two together thinking that they're all under the cosine function when they're really supposed to be kept separate. But if you just note that mentally and then rewrite it like this, then that's fine too. This one's tricky a little bit.
So the outside would be the exponent thing.
You would think.
But you know, it's really good, right?
So this is math.
Yes, I'm just.
Oh, no, my best friend lives in Missouri, and they was like, apparently exponents can have exponents now. So it's like in the same
Yeah.
part that they are.
I've seen it in problems. I've never, like, I've seen it on ACT. We just guess.
Well, this is an exponent that is also a function.
Wow.
Oh.
Cool.
It's not.
So,
Just another part of it, and not see how it's any different.
They're trying to really just say y'all just dumb. I mean, I know that.
well, this one is a little bit different because the first two that we've done, or we did one, the example that I did first, and then part B, the exponent was the outside function. In this case, the outside function is e raised to an exponent. So dealing with the exponent is happening first, that is true, but dealing with the exponent up here is different because our exponent is just a number
The other one's a function.
and this one's a function, so it looks different.
So if it's a function, you just go ahead and make it, like right now it'd be.
Yes, so taking the derivative of the outside function is the same as taking the derivative of e to the x power, which we talked about. I don't know if it was the last set of notes or not.
It's one
A
of
while
the
back.
notes, I just
Some
don't
set of
remember
notes, we
which one.
talked about it. So the derivative of e to the x is e to the x. It's the one that just stays the same.
Was derivative of exponential and logarithm.
There you go. Thanks, Dakota. So when we take the derivative of e to this big long exponent, that being our outside function, it just stays the same. So the derivative of the outside function is still e raised to w to the fourth minus 3w squared plus 9. So then we multiply by the derivative of the inside function, which would be the function that's in our exponent, w to the fourth minus 3w squared plus 9. So what is the derivative of w to the fourth? Yes. And then the derivative of 3, technically negative 3w squared, negative 6w to the first power technically, but we don't have to write that. And the derivative of 9,
You just drop it.
0, so we don't have to write that. Okay, so just rewriting this to make it look a little bit cleaner, we can write, you can reorder multiplication. So I'm going to rewrite it with this 4w cubed minus 6w first, and then e to the exponent.
Part B missing a parentheses. I didn't notice it until you had boxed it. Just before the exponent 49.
Mm-hmm. It is. Thanks.
I really wouldn't have noticed it if you hadn't have boxed it.
That's crazy.
That's crazy.
That is so crazy.
That is insane.
All of us out.
That has never happened before. Just kidding. All right, part D. Keep going.
I wonder if that's about it.
I'll cover it. If I get it, I'm gonna have it. Also, like, I'll have to see it.
Where'd that come from? Where'd that come from?
I pulled it
I
right
just
out
get
of
into the thing. I'm like, oh.
You know what? Use this on. That door. Yeah.
the
I pushed from one part to like the grocery bin up the hill, and I was exhausted. And I was like, dang, I think there's just like.
I think I'm not.
For the Pokemon's at the Walmart, their carts get way overflowed. Like out. So, okay, well, I appreciate it.
This is one line. This is one line.
I didn't do the first cross country for me. So I think it was so bad. Like it was, and I was like,
It's not reading pretty good.
because like when you look right on the. I'm like, oh,
Last time I got my
Okay,
Thursday.
This one, g of x equals the natural log of x to the negative fourth plus x to the fourth. What is the outside function? The natural log. So taking the derivative of the natural log, let's say we have the natural log of x. The derivative is 1 over x. So whatever you're taking the natural log of just gets put in a denominator under 1. So the derivative of our outside function, natural log, yep. One over what we're taking the natural log of, which is that inside function. Then we're multiplying by the derivative of the inside function, which is x to the negative fourth plus x to the fourth. What's the derivative of x to the negative fourth? Yes. Yeah, negative exponents are tricky because when you're subtracting from a positive exponent, your number decreases. When you're subtracting from a negative exponent, it stays negative and the number goes up by 1. It's odd. Okay, plus the derivative of x to the fourth, which is 4x cubed. Okay, so simplifying this just a little bit. When we multiply something times a fraction, whatever you're multiplying by just gets multiplied by the numerator. So we can just put negative 4x to the negative fifth plus 4x cubed over x to the negative fourth plus x to the fourth.
I never liked it. That answer looks so messy to me.
It does. Well, and I'll address too this negative exponent. You know, before I said we don't like to have negative exponents in our answer. But number one, we were given a negative exponent in the function to begin with. Normally, anything that is shown in an original function is fine to have in your answer as well. And then also, we can't move this term to the denominator because it has something being added to it. The only way you can move stuff around is if everything is being multiplied. So if this were negative 4x to the negative fifth times 4x cubed, we could absolutely move this to the denominator to make this exponent positive. But because it's addition and not multiplication, we can't move stuff around like that. So, yes, it does look messy, but that is our answer. Two more parts of example 2, parts E and F. Let's see, example 3 has only 3 parts. Wait.
Only 3 parts.
Oh, then there's example 4 too.
Yeah, like back then when you did, I feel like it's only 4 problems they have all work page each of work.
Okay, y equals secant of 1 minus 5x. the outside function is secant. So when we take the derivative, y prime, we do the derivative of the outside function. Anyone remember what the derivative of secant is? Go for it, Matthew.
Secant times tangent.
Yes, secant tangent.
Oh.
I've got my notes open to this. I pulled it when we started, right?
So taking the derivative of the outside function, we get secant of 1 minus 5x times tangent of 1 minus 5x. Then we have to take the derivative of the inside function, 1 minus 5x. The derivative of 1 is 0. The derivative of negative 5x, negative 5. Oh gosh. Okay, so again, we need to make sure that this negative 5 doesn't get grouped in with this trig function. So let's write it at the beginning instead. Oops.
Is the negative 5 just multiplying the secant or secant and tangent?
Technically, it's all three of these are being multiplied together. It's not that negative 5 is like being distributed. It's just like x times y times z, basically. Last part of example 1 or 2, whatever example this is.
I hope this is just example 1.
This is cosine to the 4th of t plus cosine of t to the 4th. So we did some, or at least one example in derivatives of trig functions like this, cosine or some trig function raised to an exponent before this part. So let me remind you, cosine to the 4th of t is the same as cosine of t raised to the 4th power. It's just this is just like a shorthand way of writing cosine of t to the 4th power.
None of us talked about it. Where were we gonna put it? We were just gonna put a bunch of, like, print a bunch of copies and put them in our truck. We should be really mad if we did it anywhere else. I want it sticking out our truck.
Okay, let's rewrite this then. Okay, we'll take a break after this part.
I didn't get the help with that. No one told me about it. Yeah, no one told me about it. I was like, oh, Taylor left and didn't say anything. We were literally in the same class. I was like, thanks, Taylor. I want to do something else. Then I just do it.
Okay, so I just rewrote cosine to the 4th of t. I rewrote it as cosine of t to the 4th. So we're actually going to be using the chain rule twice here. No, not yet. I just rewrote the function right now. I didn't take the derivative yet. But we have a composition of functions here. We have a trig function raised to a power. And then in this one, we have a variable raised to a power inside a trig function. So we've got to use the chain rule on both of these when we take the derivative. So just focusing on cosine of t raised to the fourth power, what is the outside function? The exponent of 4 is the outside. So when we take that derivative, the 4 comes down in front. So 4 times cosine of t, and our new exponent is 3. But then we have to multiply this by the derivative of the inside function, which is cosine of t. So the derivative of cosine is negative sine. So this is the derivative of just this first part, cosine of t to the fourth. Then we're adding the derivative of this next part, cosine of t to the fourth. It's different. You read it the same, cosine of t to the fourth power, cosine of t to the fourth power. You read it the same, but it's different. Isn't that crazy? Okay, so one way that it's different is the outside function is not the exponent this time, it is the trig function, because our exponent is on the variable inside the trig function. So the outside function is cosine. The derivative of cosine, we've already said, is negative sine. And the inside function stays the same. So negative sine of t to the fourth. And we multiply that by the derivative of the inside function, which is t to the fourth. Oops, sorry, 4t cubed is that derivative. Okay, that's the difficult part. Now let's just rewrite this, make it a little nicer looking. This first term, we have a positive times a negative. That's going to end up being negative. So we'll just go ahead and put the negative out in front. Okay, so I put sine first. Normally sine comes before cosine. That's just how it's normally written. And then writing cosine of t raised to the third power, I just rewrote it in the shorthand way, put the exponent here. So it's cosine cubed of t. Okay, in the second part, we have a negative times a positive. So that's going to also be negative. So instead of writing plus a negative, we can just write it as minus. And we'll put 4t cubed first times sine of t to the fourth. Okay, let's take 5 minutes and then we'll do a little bit more. We won't get to practice problems today, but we still have a few examples that I want to work. But we'll take a quick break first.
It's like, well, how do I? You just don't.
Okay. I'm gonna write out some general rules. With regard to the examples that we just worked. Those are good general rules too, though. Be nice.
I hated that.
Expectations.
It would work for like a week and then after that, no one cared. I'm like,
Yeah, she wanted, I was like,
what's your definition of teamwork?
Yeah, it's like, well, it could be different from this person.
Why are we?
Oh,
Teamwork.
Let me define teamwork. Working
Abandon
together.
y'all.
Working together.
There's so many people who don't know what teamwork
Yes.
For what? For astronomy.
Oh.
Just me.
After
Everyone.
that moment, I was like,
means. Yeah, I would not go to school. I would like leave.
let's do this. I was trying.
Okay. First one, part A, f of x equals g of x raised to the n power. So we've got a function raised to an exponent, which we've done a few of these. We said the outside function is the exponent. And the inside function is g of x, whatever's being raised to the power. So the derivative then, f prime of x, looks like this. We bring the exponent down in front, so n comes down in front. G of x stays the same. We subtract 1 from the original exponent, so our new exponent is n minus 1. And then we multiply by the derivative of g of x, g prime of x. It's the same thing that we've been doing. It's just written as a general rule instead of as an example. Yeah. General rules that we've already used, we just are writing them as general rules now. So part B, f of x equals e to the g of x. The outside function is e. Technically, the outside function is e raised to a power. I'm going to put a little caret to symbolize that. And the inside function is the exponent, g of x. So then, so the derivative f prime of x is going to be, okay, stay with me. It's g prime of x times e to the g of x powered. So this is the end result. When we worked the example, we took the derivative of the outside function first, which would be e to the g of x. Then we multiplied by the derivative of the inside function. But then when we wrote our final answer, we reordered it. So that's what we did for this general rule, is the derivative of the inside function just gets written first, and then e to the g of x stays the same. Last one, natural log. So the outside function is the natural log. The inside function is g of x. So f prime of x, the derivative, when we worked this one out, our end result was g prime of x over g of x. Oops, not. So when we were working it out, we ended up with 1 over g of x times g prime of x. But then when we wrote our final answer, it was g prime of x over g of x. Because we just moved this g prime of x to the numerator. Okay, we got some more examples. So this is example 3.
Mine don't have the place for these times. It just has no.
You just announce your graduation.
Yeah, like I didn't necessarily mean you.
You're sharing the news.
And then Western High School and then make them split. And I'm like, they're gonna know kind of like, yeah, they probably don't have any. I like face everybody. But I'm sending out some invitations.
We can only have 8 people, right?
That's as far as I know, yeah.
It might change though. From now on.
Yeah, it's dependent on ASU's policies.
Because if that list.
Well, yeah, I'm ready.
Announcement, then that's
We wait from.
Hopefully.
Yeah.
Yeah.
Here's
Here's my cash app. My PayPal, my PayPal. I need a new computer soon, so. Yeah, make sure. That's probably what this next check is going to.
Hold on.
When I have my computer, okay. Don't make it.
Okay, sorry, I had to erase. This is f of z equals sine of z times e to the z. Yep, e to the z. Z times e to the z. I sound like a rapper yet. All right. So using the chain rule, because we have a function inside a function, f prime of z, what is the outside function? Sine. What's the derivative of sine? Cosine. And the inside function stays the same. Now, the inside function is z times e to the z. So the inside function is actually two functions being multiplied together, z times e to the z. So to take the derivative of z times e to the z, these two functions that are being multiplied together, we have to use the product rule. So within the chain rule, we're now using the product rule. So to take the derivative of z times e to the z, if this is our first function and this is our second function, remember the product rule is the derivative of the first function, which in this case is z, times the second, the first function is z, which means the derivative of the first function is 1, times the second function as is. Let me just write it. F times g, f prime times g plus f times g prime.
Oh, that, okay.
Yep. And this is our f, this is our g. So the derivative of the first function is just 1. 1 times anything is that thing. We don't really have to write that. But then we leave the second function as is, e to the z. Plus the first function as is, which is z, times the derivative of the second function. And the derivative of e to the z is still e to the z. So to take the derivative of the inside function, we had to use a product rule. There's not really much that we can do to simplify this. We just want to write this for this part first before the cosine. So e to the z plus z times e to the z, cosine of z to the e times e to the z. Good grief. I know.
Like I knew this would happen as long as you wrote it down the first.
Yep. Yeah.
No, it made this probably just as fun with this one.
Yeah.
Okay, this one's gonna be really fun. It'll be our last one for today. Was that on my door?
He said, oh wait, I forgot.
There's been lots of dad jokes today. Like Denelli just trying to stay positive instead of saying the negative number. 2x squared, yes. And then that whole thing in the denominator is raised to the third power. Y equals x cubed plus 4, all raised to the fifth. over 1 minus 2x squared, all raised to the third. So first and foremost, this is a quotient. It's two functions being divided by each other. So we're going to have to use the quotient rule to find the derivative. Within the quotient rule, we're going to have to use the chain rule because this is, in the numerator, we have a function inside of a function, and in the denominator, we have a function inside of a function. Are we ready? So let's be reminded of the quotient rule. It is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. Okay, so y prime. We're going to follow this formula, but within this, we're going to have to use the chain rule. So like the very first thing we have to do is take the derivative of the numerator. And the numerator is a function inside of function. So we have to use the chain rule to find the derivative of the numerator. So the outside function is our exponent. So let's take the derivative of the outside function. The 5 comes down in front. The inside function stays the same. Our new exponent is 4. Times the derivative of the inside function, which is x cubed plus 4. So the derivative of x cubed is 3x squared. The derivative of 4 is 0. Plus 0 does nothing, so I'm not going to write it. What we've just done here is this f prime. We took the derivative of the numerator. So now that gets multiplied by the denominator as is. 1 minus 2x squared cubed. So we've just done this part of the formula, f prime times g. We're done with that. Then we're subtracting f times g prime. So the numerator as is, which is x cubed plus 4 raised to the 5th power, times the derivative of the denominator, which is a function inside a function. So we've got to use the chain rule to find the derivative of the denominator. So the outside function in the denominator is this exponent of 3. So when we take the derivative, the 3 comes down in front, the inside function stays the same. We subtract 1 from the exponent, so our new exponent is 2. And that gets multiplied by the derivative of the inside function. So the derivative of 1 minus 2x squared. Well, the derivative of 1 is 0, so I'm going to leave that off. The derivative of negative 2x squared, the 2 comes down in front, we get negative 4x to the 1st power, but when the exponent is 1, we don't have to write it. So we're finished with f times g prime. So all of that gets put over the denominator squared. So 1 minus 2x squared cubed squared. Yeah, like solving for x.
Yeah.
Yeah. Let's see. Yeah, it can. Okay, I see. Within this function, well, okay. I'm trying not to confuse y'all about what I'm gonna do. We've got some common factors in this part and this part. Okay, common factors would be x cubed plus 4. We've got x cubed plus 4 here, x cubed plus 4 here. This one's raised to the 4th power, this one's raised to the 5th power, but it's still the same factor. We also have 1 minus 2x squared in both of these. So we can factor those out of the numerator, and we'll factor out as many as we can, and we can only factor out as many as the smallest exponent. So the exponent here is 4, the exponent here is 5, so we can only factor out 4. So we're going to factor out x cubed plus 4 to the 4th power. We're going to do the same with 1 minus 2x squared, but we can only factor out the smaller exponent, which in this case is 2. So we're factoring out 1 minus 2x squared squared. So we're doing the opposite of distributing. We're pulling things out. So what we're going to be left with in this first term, what we're left with is 5. We factored out all 4 of these, x cubed to the 4ths. We're left with 3x squared. And we factored 2 out of the 3 of these factors. So what we're left with is 1 of these factors. 1 minus 2x squared to the 1st power, but when the exponent is 1, we don't have to write it. No. No, because we're subtracting what's left from here. We factored out 4 of the 5 of these factors. So we have 1 of these factors left, x cubed plus 4 to the 1st power, technically, but we don't have to write it. We're left with this factor of 3. We factored out both of these, 1 minus 2x squared. We factored both of those out. But we are left with negative 4x. In the denominator, when you raise a power to a power, like this cubed power squared, you multiply those exponents. So what we have in the denominator is 1 minus 2x squared to the 6th power. Okay, we have some more still. This is just a lot to simplify. That's okay. We can do hard things. You can. Don't say that. Okay, we have I know. Okay, let's just do it. We have x cubed plus 4 to the 4th. That's going to stay the same. We have 1 minus 2x squared, but we also have some of those in the denominator. 1 minus 2x squared, we have 6 of them. So these 2 will cancel out with 2 of these, and that will become 4. So we're not even going to write those. Inside this bracket, we can do some stuff. We can multiply 5 times 3x squared is 15x squared. We can then distribute that to both of these. So 15x squared times 1 is 15x squared. 15x squared times negative 2x squared is negative 30x to the 4th. Minus, we can do the same thing here. We'll multiply these and then distribute. So 3 times negative 4x is negative 12x. Let's see, I'm going to go ahead and keep this a bracket actually. Negative 12x times x cubed is negative 12x to the 4th. Negative 12x times 4 is negative 48x. Over 1 minus 2x squared now to the 4th. There's still more. We can still do more. Okay. X cubed plus 4 to the 4th is going to stay. Let's distribute this negative. Mm-hmm.
Got here 30 minutes early, we're trying to be courteous.
Dude. Yeah, I can see 5 minutes.
Like,
Sorry, it is.
yeah, it's like switched.
Okay, yeah. We'll finish it next time. Shoot.
Most of that problem with just staring, looking at